Since ancient times, humans have always been curious about the planets, stars, and their motion. They also had different ideas and beliefs about that. At that time, Nicholas Copernicus, a Polish astronomer, proposed a specific planetary model of the solar system, where he stated that the Sun is the center of the solar system, and all the planets revolve around it. But his theory was rejected by the Church. It is also notable that, amongst its supporters was Galileo Galilei, had to face various prosecutions for his beliefs. At the same time, a nobleman from Denmark, Tycho Brahe, spent his entire life recording the observations of the planets, with his naked eye. He accumulated various information about the motion of the planet. All of his compiled data was later analyzed by his assistant, Johannes Kepler, and he arrived at 3 elegant laws of planetary motion. Now, these laws are popularly known as Kepler's laws of planetary motion. In this tutorial, we will uncover the details of these laws. So let's start. To describe the motion of the planets, Kepler arrived at 3 elegant laws of planetary motion. These are the law of orbits, the law of areas, and the law of time periods. Kepler's first law of planetary motion. Also known as the law of orbits. Kepler's first law states that each planet revolves in an elliptical orbit around the Sun, and the Sun is in the focus of that ellipse. This law means that the orbit of a planet around the Sun is an ellipse, and not an exact circle. So from this law, we know the geometrical shape of the orbits. An ellipse has 2 foci, and the Sun is at one of the 2 foci of the ellipse. The point in this ellipse, where the planet is closest to the Sun, is called the perihelion, and the point at which the planet is farther from the Sun, is called the aphelion. These elliptical orbits of the planets are responsible for the occurrence of seasons. Now if we talk about the ellipse, then it has 2 axes, a major axis, and a minor axis. The major axis is the longest diameter of the ellipse. It goes through the center from one end to the other, at the broader part of the ellipse. Whereas the minor axis is the shortest diameter of the ellipse, that crosses through the center at the narrowest part of the ellipse. Half of the major axis is called the semi-major axis, usually denoted by small a, and half of the minor axis is called the semi-minor axis, denoted by small b. An ellipse is a shape that resembles a flattened circle. How much the circle is flattened is expressed by its eccentricity, which is represented by the Greek letter, epsilon. The relationship between eccentricity, along with these semi-major and semi-minor axes is, epsilon is equal to, root over 1 minus, b squared by a square. The eccentricity of an ellipse varies from 0 to 1. If it is 0, the ellipse becomes a circle, and if it is 1, then the ellipse becomes a parabola, or essentially a flat line. So for an ellipse, eccentricity ranges from 0 to 1. Now if we talk about the planetary orbits, then only Pluto has a large eccentricity. Here is a table showing the eccentricity of the orbits of the planets in our solar system. Kepler's second law of planetary motion. Also known as the law of areas. Kepler's second law states that the straight line connecting the Sun and a planet crosses equal areas in equal intervals of time. Basically, planets do not move with constant speed along their orbits, that is, their speed varies from place to place. So the line joining the centers of the Sun and the planet sweeps out equal parts of an area in equal intervals of time. As we already know, the point where the planet is closest to the Sun is called the perihelion, and the point where the planet is farther from the Sun is called the aphelion. Hence by Kepler's second law, we can clearly understand that the planet moves fastest when it is at perihelion and slowest when it is at aphelion. Kepler's third law of planetary motion. Also known as the law of periods. Kepler's third law states that the square of the time period of the revolution of a planet around the Sun in an elliptical orbit is directly proportional to the cube of the semi-major axis of the ellipse. Kepler's third law implies that the period for a planet to orbit the Sun increases rapidly with the radius of its orbit. Thus we find that Mercury, the innermost planet, takes only 88 days to orbit the Sun. The Earth takes 365 days, while Saturn requires 10,759 days to do the same. Although Kepler did not know about gravitation when he came up with his three laws. But these laws were very important in developing Newton's universal law of gravitation. Kepler and his theories are important for better understanding the dynamics of our solar system and as a springboard for new theories that more accurately approximate the orbits of our planets. Newton's law of gravitation. Since ancient times, scientists have always been curious about planets, stars, and their motions. Nicholas Copernicus was the first to say that the Sun is stationary and the Earth revolves around the Sun. Later, the German scientist Johannes Kepler discovered three elegant laws of planetary motion, which are popularly known as Kepler's laws of motion. By analyzing these laws, Sir Isaac Newton determined the nature of the force of attraction between the Sun and the planets. This force of attraction is called gravitation, which not only acts between the Sun and the planets, but also between any two objects in the universe. Newton observed that all the objects in the universe attract each other with a certain amount of force, but in most cases the force is too weak to observe due to the very large distance of separation. The range of this force is infinite, but the force becomes weaker as the objects move away. To measure this gravitational force, Newton introduced a law known as Newton's law of gravitation. The law states that any two objects in this universe attract each other along their connecting straight lines. The magnitude of this gravitational attraction is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematical expression. Let the distance between two objects of mass m1 and m2 be r. If the force of attraction between the two objects is denoted by F, then according to Newton's law of gravitation, F is directly proportional to m1 into m2. And F is inversely proportional to r square. By combining these two formulas we get F is proportional to m1 into m2 divided by r square. Now we need a constant to replace the proportionality symbol and place an equal sign there. This constant is taken here as g, so the formula is written as F is equal to g m1 m2 divided by r square. This is the formula for the gravitational attraction between two objects in this universe. Here g is known as the universal gravitational constant. Now, if capital M is taken as the mass of the Earth, and small m is the mass of any object present on the surface of the Earth, then the gravitational attraction between them, F is equal to g mm by r square. Where r is the radius of the Earth. Since the object is on the surface of the Earth, the separation is taken as the radius of the Earth. Gravitational constant. If we want to define the gravitational constant g, then all the quantities present in the formula, except the constant g and f, must be taken as unit values. So, if we take unit mass and unit distance, then we get g equals f. This simply defines the gravitational constant as follows. The gravitational constant is the force of attraction between two objects of unit masses separated by unit distance. Unit and dimension of g. From equation number 3, we can write the unit of g is equal to the unit of f into unit of r square divided by unit of m square. We know, in the SI unit system, the unit of mass is kilogram, the unit of distance is meter, and the unit of force is Newton. So the SI unit of g is Newton meter square per kilogram square. Similarly, we can write the CGS unit of g as dyne centimeter square per gram square. Again, using equation number 3, we can write the dimension of g is equal to dimension of f into dimension of r square divided by dimension of m square. That is, mlt minus 2 into L square divided by m square. Or m inverse, L cube, t minus 2. If we talk about the magnitude of g, then it is determined by various experiments. In the SI unit system, we find G is equal to 6.67 into 10 to the power minus 11 Newton meter square per kilogram square. And in the CGS unit system, we find G is equal to 6.67 into 10 to the power minus 8 dyne centimeter square per gram square. That means, if we separate two objects of mass 1 kilogram by a distance of 1 meter, the gravitational force between them will be 6.67 into 10 to the power minus 11 Newton. According to Newton's law of gravitation, the force of attraction between two objects depends only on their masses and their distance. This force of attraction does not depend on the state of the objects, chemical composition, temperature, the medium between them, etc. The law of gravitation applies equally to the small distances between earthly bodies, and very large distances such as the distances between planets and stars. With the help of this law, it is possible to clearly explain the motion of the planets around the Sun. For these reasons, the law of gravitation is considered to be universal, and the gravitational constant is called the universal gravitational constant. However, according to Einstein's theory of relativity, the mass of an object depends on its velocity. The distance between two objects also depends on the velocity of the observer, that is, the distance between two objects measured by a stationary observer will not be the same as that measured by a moving observer. And also Newton's law of gravitation does not apply to microscopic distances, such as atomic and nuclear distances. For these reasons, Newton's law of gravitation can no longer be called a universal law. However, even in Einstein's theory, the universality of the gravitational constant G is not undermined. What is gravitational field? Before understanding the gravitational field, let's look at an example, which almost all of us have done in our lives. Once you understand the example I shared with you, it won't take you long to understand the gravitational field. When we place a nail next to a magnet, we see that the magnet attracts the nail. But the magnet can attract the nail only when the nail is kept within a certain region of that magnet. If the nail has been placed some distance from that certain region, the attractive force can no longer affect the nail. That region is the region of the magnet, known as the magnetic field of that magnet. If we place a magnet instead of the nail, we can see the repulsion effect also. However, from this example, we can clearly understand that a magnet has a region in which the magnet can exert the force of attraction or repulsion. Similarly, in the universe, any object, it may be a planet, star, or anything, has a region where another object experiences an attractive force when it enters. That region is called the gravitational field. But here it should be remembered that, in this case, only attractive force acts, no repulsive force acts. For example, due to the gravitational field of the Earth, any object in this field experiences an attractive force towards the center of the Earth. Now if we want to define the gravitational field, then it can be defined as follows. The gravitational force acting on a unit mass of an object, at any point in space due to another object, is called the gravitational field of that object. In physics, the gravitational field is a model that is used to explain the influences that a massive object extends into the space around itself. In reality, the gravitational field of any object extends to infinite distances, but the region after which the gravitational force becomes negligible, that region is no longer regarded as the gravitational field of the object. Now, it is important, not only to mark a region as a gravitational field of an object, but also to measure the gravitational effect at each point in that region. That is why we measure the gravitational field intensity at a particular point in that gravitational field. Measurement of the gravitational field intensity. From Newton's law of gravitation, we know that the gravitational force between two objects of masses capital M and small m, separated at a distance of r, is F is equal to gmm by r square. Now for an object of mass capital M, we need to determine the gravitational field at a distance of r from its center. So, if we take small m equals 1, then according to the definition, we will get the gravitational field due to the object of mass capital M, at a distance of r from its center, and that is E is equal to gm by r square. So from equations number 1 and 2, we get, E is equal to, F by m. This is the measure of the gravitational field intensity. From the view of gravitation, this gravitational field intensity is identical to the acceleration due to gravity. So sometimes this gravitational field represents by g, that is, g is equal to, F by m, or gm by r square. Since force and acceleration are both vector quantities, the gravitational field intensity is also a vector quantity. The direction of this field intensity is always worked towards the center of the object. Unit of gravitational field. From equation number 3, we can write, the unit of the gravitational field is equal to the unit of force divided by the unit of mass. So the SI unit of gravitational field is Newton per kilogram, or meters per second squared. And the CGS unit of gravitational field is dyne per gram, or centimeter per second squared. Dimension of gravitational field. From equation number 3, we can also write the dimension of the gravitational field is equal to the dimension of force divided by the dimension of mass. That is, mLT minus 2 divided by m, or LT minus 2. So the dimensional formula of the gravitational field is equal to m0 L1T minus 2. What is gravitational potential? The amount of work that an external agent has to do to bring an object of unit mass from an infinite distance to a point in the gravitational field is called the gravitational potential of that point. At an infinite distance, that is, where there is no gravitational field, the gravitational potential is taken to be zero. When an object of unit mass is brought from there to a point in the gravitational field, the work performed is always due to the gravitational force. Since the work performed by the force is negative, the gravitational potential is also negative. That is, the gravitational force is always a force of attraction, so the gravitational potential at any point in the gravitational field is negative. The symbol we use to represent the gravitational potential is capital V. Measurement of the gravitational potential. Let's assume an object of unit mass, moving freely toward an object of mass capital M. Here the object of unit mass is attracted by m, and moves toward it by a small distance dr. This displacement dr is the result of work W, exerted by the gravitational field generated by m. So dW is equal to F dot dr. Now, we also know from the definition of the gravitational field, the gravitational force due to the object of mass m, on a unit mass at a distance of r from its center, F is equal to gm by r square. So from equation number 1 and 2, we get the work done dW is equal to gm by r squared dot dr. Now, to bring the unit mass from infinity to a position r, the work done, or the gravitational potential V, is equal to, the integral to, infinite to r, of dW. Or integral to, infinite to r, of gm, by r square, dot dr. Now solving this equation we get, V is equal to, minus gm by r. This is the measure of the gravitational potential. The relation between gravitational potential and gravitational field. The gravitational potential V is equal to the integral of E dot dr, or E is equal to dV, dr. This is the relation between gravitational field and gravitational potential. Gravitational potential is a scalar quantity, because it has only magnitude, no direction, just like work. Unit of gravitational potential. From the definition, we find that the gravitational potential is equal to, the work done to bring an object from infinity, divided by the mass of the object. So the unit of the gravitational potential is equal to the unit of work, divided by the unit of mass. Therefore the SI unit of gravitational potential is, joule per kg. And the CGS unit of gravitational potential is erg per gram. What is gravity? Gravity is the force by which a planet or other body draws objects, toward its center. As a result of this gravity, when an object is released from a distance, above the surface of the Earth, the object moves towards the center of the Earth. Anything that has mass also has gravity. Objects with more mass have more gravity, and objects with less mass have less gravity. Gravity also gets weaker with distance. So the closer objects are to each other, the stronger their gravitational pull is. Newton clearly stated that any two objects in this universe attract each other with a certain amount of force, but he could not explain what caused this attractive force. That is, he told us about the strength of gravity, but he never found the source of gravity. This concept was fulfilled by Einstein's general theory of relativity. Einstein said that, in reality, gravity is not a force, but it is actually the same thing as acceleration. According to this theory, matter causes curvature in spacetime. Wherever there are matters in the universe, there will be curves in spacetime. More matter will create more curvature, and less matter will create less curvature in spacetime. For this curvature, the objects in the universe attract each other. This is why planets are orbiting the Sun. This curvature is the source of gravity. Now let's understand the concept of gravity with an example. Suppose we have a piece of fabric, a large ball, and two smaller balls. Now, if we put the big ball on the fabric, then what will happen? It will push the fabric inwards. Again, if we put two small-sized balls on that fabric, then you will see that both those balls also push the fabric inward, but less than the big one. As the big ball has pushed the fabric more inward, so it will pull the small ball towards its center. Einstein said that, this is why the objects in the universe attract each other. This concept of gravity will be more clearly understood if you study Einstein's general theory of relativity more deeply. For this, we will make a separate video on general relativity, but for now, we will only discuss acceleration due to gravity. Acceleration due to gravity. The acceleration gained by a freely falling object, due to the gravitational force, or gravity, is called acceleration due to gravity. The symbol we use, to represent the acceleration due to gravity, is small g. Measurement of acceleration due to gravity. Let us consider, the mass of the Earth is capital M, and the radius of the Earth is capital R. If an object of mass small m, falls freely at a distance of r, from the center of the Earth, due to the gravitational force, or gravity, then according to the Newton's law of gravitation, F is equal to gmm by r square. And also if the object gained an acceleration g, due to the force F, then according to Newton's law of motion, F is equal to mg. From equations number 1 and 2, we get, mg is equal to gmm by r square. Now solving this equation we get, g is equal to gm by r square. This is the formula for the measurement of the acceleration due to gravity. For any point on the surface of the Earth, small r is equal to capital R. So from equation number 3, we can write g is equal to gm by capital R square. This is the formula for measuring the acceleration due to gravity, on the surface of the Earth. From this relation, we find the average value of g, on the surface of the Earth. In the SI unit system, we find the value of g, is equal to 9.806 meter per second square, which is nearly 9.8 meter per second square. In the CGS unit system, the value of g, is equal to 980.6 centimeter per second square, which is nearly 980 centimeter per second square. Variation in acceleration due to gravity. Acceleration due to gravity is not a constant quantity. Its value changes for various reasons. For example, as the Earth is elliptical, the value of g varies in different parts of the surface of the Earth. The value of g varies at different heights from the surface of the Earth. Similarly, the value of g varies at different depths from the surface of the Earth. It also varies in different parts of the Earth's surface, due to the rotational motion of the Earth. Variation in acceleration due to gravity with heights. Let the Earth be a sphere of radius r, and mass m. We know the acceleration due to gravity on the surface of the Earth is g is equal to gm by r square. We will determine the formula for the acceleration due to gravity at a point above the surface of the Earth. So consider any point at the height h above the surface of the Earth. The acceleration due to gravity at that point is gh is equal to gm by r plus h whole square. Now dividing equation number 2 by equation number 1, we get gh is equal to r squared divided by r plus h whole square into g. This relation clearly shows that gh less than g. This means that as we continue to move above the surface of the Earth, the acceleration due to gravity decreases. Now, gh is equal to r square divided by r square into 1 plus h by r whole square into g. By solving this equation we get gh is equal to g into 1 minus 2h by r. This is the formula for variation in acceleration due to gravity with heights. Variation in acceleration due to gravity with depth. Again, let the Earth be a sphere of radius r and mass m. We know the acceleration due to gravity on the surface of the Earth is g is equal to gm by r square. If ρ is the density of the Earth, and capital V is the volume of the Earth, then the mass of the Earth, capital M is equal to ρ into V. We know V is equal to 4 by 3 pi r cube. Therefore capital M is equal to 4 by 3 pi r cube ρ. Now substituting the value of m in equation number 1, we get small g is equal to capital G by r square into 4 by 3 pi r cube ρ. By solving this equation we get g is equal to 4 by 3 pi r ρ g. Now we will determine the formula for the acceleration due to gravity at a point below the surface of the Earth. So consider any point inside the Earth, below the Earth's surface at depth d, in which, if an object is placed, it will only experience the force due to the portion of the Earth of radius r minus d. Now, again let capital M prime be the mass of the Earth, of the portion of radius, r minus d. Then the acceleration due to gravity at that point is, gd is equal to gm prime, divided by r minus d whole square. But, m prime is equal to 4 by 3 pi into r minus d whole cube into ρ. Substituting the value of m prime in equation number 3, and after solving we get gd is equal to 4 by 3 pi into r minus d into g ρ. Now dividing this equation number 4 by equation number 2, we get gd is equal to 1 minus d by r into g. This is the formula for variation in acceleration due to gravity with depth. It clearly shows that the value of acceleration due to gravity decreases with depth. At the center of the Earth, where d is equal to r, the acceleration due to gravity is 0. What is escape velocity? The minimum velocity that a body must have in order to escape the gravitational attraction of a particular planet or other objects is called escape velocity. Now, let's understand the concept of escape velocity in one shot. If an object is thrown vertically up from the surface of the Earth, the object rises to a certain height and falls to the Earth's surface due to the gravity of the Earth. At maximum height, the velocity of the object is 0. The faster the object is thrown, the greater the height of the object it reaches, after which its velocity becomes 0. As the velocity increases gradually, a state is reached where the object's velocity is no longer 0. That is, it no longer returns to the surface of the Earth. In this case, the object moves further away from the Earth, and the gravitational attraction of the Earth on the object becomes less and less. So we can say, the object reaches an infinite distance from Earth. The minimum velocity required for this to occur is the escape velocity. It is notable that the concept of escape velocity applies not only to objects launched from the Earth, but also to objects launched from the surface of any planet or satellite. Measurements of escape velocity. Let us consider, the mass of the Earth is capital M, and the radius of the Earth is capital R. The gravitational force on an object of mass small m, at a distance of small r, from the center of the Earth, capital F is equal to gmm by r square. Now the work done, to move the object to a very small distance dr, along the line of action, against this gravitational attraction, dw is equal to F dot dr or gmm by r square into dr. Hence the amount of work done, to send the object to an infinite distance, from the surface of the Earth, w is equal to, integral to, r to infinite of, gmm by r square into dr. By solving this integration, we get the work done, w is equal to gmm by r. Again, let's v is the escape velocity of the object on the Earth. Then the initial kinetic energy of the object, Ki is equal to, half mve square. If this kinetic energy, becomes equal to the above work, then the object escapes from the gravitational pull of the Earth. Therefore, half mve square is equal to, gmm by r. Now solving this equation we get, ve is equal to, root over, 2 gm by r. We also know, the acceleration due to gravity at the surface of the Earth, g is equal to, gm by r square. So capital Gm is equal to, small g into capital R square. Now by substituting the value of Gm, in equation number 1, we get Ve is equal to, root over, 2gr. This is the formula for measuring the escape velocity, on the surface of the Earth. We know the acceleration due to gravity on the surface of the Earth, small g is equal to, 9.8 meter per second square. And the radius of the Earth, capital R is equal to, 6,400 km, or 6.4 into 10 to the power 6 meters. Now substituting these values, in equation number 2, we get, Ve is equal to, 11,200 meter per second, or 11.2 km per second. This value is the measure of escape velocity, of any object on the surface of the Earth. This means, if an object of any mass, is thrown upwards, from the Earth's surface with a speed of, 11.2 km per second, the object goes out of the Earth's gravitational field, that is, it does not return to the Earth. In simple words, if an object in space, revolves around a star, we call it a planet, and if it revolves around a planet, then we call it a satellite. When it comes to the classification of satellites, it is divided into two main categories, one is natural satellites and the other is artificial satellites. We all know that, the satellites that are found in nature, are called natural satellites. For example, the Moon is the only natural satellite, of the planet Earth. Similarly, Jupiter has 67 such natural satellites, and so on. But all the satellites that are created by humans, are called artificial satellites. In this tutorial, we will uncover the details of artificial satellites. As we discussed earlier, the motion of various planets or satellites, can be determined by Newton's law of motion, and Newton's law of gravitation. From this, scientists believe that, if any object launched from the Earth, can be given the proper speed, at the proper distance from the Earth, then the object will orbit the Earth, like the Moon. Putting this idea into practice made it possible, to launch the first artificial satellite, Sputnik 1, on October 4, 1957. Today, technology has advanced so much, that it is possible to place artificial satellites, around not only the Earth but also other planets. A satellite is launched vertically, or eastwards from the Earth's surface by means of a rocket. With the help of rockets arranged behind the satellite, the direction of its motion is changed in such a way, that the satellite can attain a certain level of horizontal velocity, after reaching a certain height. Then it is placed in a certain orbit, and starts to circle the Earth. Applications of artificial satellites. Basically, artificial satellites are used for communication, weather forecasting, military use for spying on enemy troops, and collection of information about the natural resources of the Earth, other planets, and outer space. Types of artificial satellites. Based on the satellite's direction of motion and distance from the Earth's surface, artificial satellites are classified into two categories: geostationary satellites and polar satellites. Geostationary satellite. Artificial satellites that revolve in the same direction as Earth in their predetermined orbits, about 35,800 kilometers above the Earth's surface, are called geostationary or geosynchronous satellites. Some examples of such satellites are INSAT, or Indian National Satellite System; GEOS, or Geostationary Operational Environmental Satellite of USA, Mediasat of Europe, etc. These are high-orbit satellites. Basically, they are used for communication and weather forecasting, like measuring cloud top temperatures, water vapor, measuring land temperature, vegetation coverage, and facilitating cyclone path prediction, etc. Polar satellite. Artificial satellites that orbit the Earth, in a north-south orbit, crossing the north and south poles, and are about 500 to 800 kilometers above the Earth's surface, are called polar satellites. For example, Landsat, NOAA, SPOT, and ERS are a few examples of polar satellites. These are low-orbit satellites. Basically, they are used to study the universe, help forecast the weather, transfer telephone calls over the oceans, assist in the navigation of ships and aircraft, monitor crops and other resources, support military activities, etc. Actually, any artificial satellite obeys Kepler's law. Hence, the orbit of an artificial satellite may also be elliptical or circular, like the orbit of a planet around the Sun, or the orbit of a satellite around a planet. However, since the eccentricity of the orbits of artificial satellites is quite low in most cases, assuming the orbits are circular does not lead to significant errors in calculations. Orbital velocity of artificial satellites. The velocity at which the satellite orbits the Earth is called the orbital velocity of the satellite. Now we will determine the formula for the orbital velocity of an artificial satellite orbiting the Earth. So let us consider the mass of the Earth as capital M, the radius of the Earth capital R, the mass of the artificial satellite as small m, the orbital velocity of the satellite as small v, and the height of the orbit from the surface of the Earth is small h. Hence the distance of the satellite from the center of the Earth, that is the radius of the orbit, small r, is equal to capital R plus h. Let's assume the orbit to be circular, then the centripetal force is equal to mv squared by r, or mv squared divided by capital R plus small h. In fact, the gravitational force between Earth and satellite provides this centripetal force for orbiting the Earth. From Newton's law of gravitation, we know gravitational force F is equal to gmm by r square. Therefore, mv squared by r is equal to gmm by r square. By solving this equation we get, small v is equal to root over gm by capital R plus small h. This is the formula for the orbital velocity of an artificial satellite orbiting the Earth. We also know the acceleration due to gravity at the surface of the Earth, small g, is equal to gm by r square. So capital Gm is equal to small g into capital R square. Now by substituting the value of gm in equation number 1, we get small v is equal to root over small g, capital R square by capital R plus small h, or v is equal to capital R into root over small g by capital R plus small h. This is also the formula for the orbital velocity of an artificial satellite orbiting the Earth. Period of revolution of artificial satellites. The time it takes to travel one complete orbit around an object is called the period of revolution of artificial satellites. If the period of revolution of the satellite is t, the distance traveled by the satellite in this time is equal to the circumference of the orbit, which is 2 pi into small r, or 2 pi into capital R plus small h. Therefore, capital T is equal to 2 pi into capital R plus small h by v. Now substituting the value of v in equation number 2, and after solving we get capital T is equal to 2 pi by capital R into root over capital R plus h whole cube by small g. This is the formula for the period of revolution of artificial satellite. Weightlessness in artificial satellites. Astronauts always feel weightless in an artificial satellite of the Earth. But on a natural satellite, like the Moon, astronauts do not experience weightlessness, because the Moon has more mass and exerts a gravitational force on them. In artificial satellites, the mass of the satellite is less, so it exerts a less gravitational force on the object, due to which the astronaut feels weightless. But it must be remembered that the attractive force of the Earth, acting on the artificial satellite, or the astronaut inside it, can never be zero. If this force were zero, there would be no question of the satellite orbiting the Earth, because then it would not be possible to provide the centripetal force necessary for orbiting. So an object being weightless means the reaction force acting on it is zero, but the gravitational force is not zero. If you enjoy our videos, then don't forget to like, share, and subscribe.